This is an expert on Isabelle. Isabelle is a theorem prover assistant, same as Lynn, but it is a different one. And we are lucky to have an expert on a different system. So she's going to give us an introduction to how to do formalized mathematics in Isabelle.
Thank you. So my aim for this talk, I know it's listed as a research talk, but really probably be more of a tutorial talk, and then maybe we'll see how we go for time, and at the end I might touch on a little bit of the research that I did using Isabelle for formalized maths. So what I'm planning to cover, basically give you a little bit of history, particularly for those who are new to formalization in mathematics, around kind of the different proof assistants out there. A bit of an overview of what Isabelle, as a proof assistant is. We'll go through a few examples. If anyone wants to try something out, I did put the link in the Tulip chat as well as some of the files, so you're welcome to have a go. And if anyone wants to, ask me anything about those after the session as well, you're very welcome to. And finish off. Yeah, that's the link. If you haven't got it already, download generally works fairly well, but not picking any guarantees. Just for those who are fairly new to formalization, this is a little bit, I guess, of history as to where these different proof assistants came from. That if you go to a conference or you go to any venue talking about formalized mathematics, and these might be the different kind of proof assistants you hear mentioned. Mazar, Cock or Rock, depending on it's been renamed, Whole Light, Isabelle Whole, and of course, Lean, which we all know quite well at this point. And of course, these are some of the results that you may have heard about in the field that kind of happened before Lean came into the picture as well. And we started to see some really big results in the last kind of 10 years. But these are historically kind of the results that were really the initial milestones that started to show that proof assistants were really quite capable of doing some pretty significant research theorems. And in cases like the full color theorem or the Kepler conjecture, actually giving some level of guarantee that the author may not have had previously. Okay. Most of these proof assistants have decent mathematical libraries. They're often a little different to something like MATLAB. MATLAB's quite unique in that it's very much all integrated, which is definitely an advantage from a mathematics standpoint. But all of these do have different levels and amounts of mathematics, often integrated with different amounts of computer science results in there as well. So there are many proof assistants out there. Like, I think there's a huge archive of them. There's more still being developed today. These are the main ones that you hear about, I think, in terms of mathematics. So yeah, I'm happy to make these slides available if anyone wants some links. So getting to Isabelle in specifically. So Isabelle first came out in the 1980s. It came out of something known as kind of the Edinburgh LCF kind of foundation, which also led to a few different whole-based theorem provers. It was mainly a kind of the initial development phase very much in the 1990s, jointly led between Cambridge and Munich, which are still kind of the two centers for Isabelle as a proof assistant today. And already what we start to see in Isabelle in the 1990s were some pretty powerful automation tactics. So things like auto as a tactic, which we'll see later, that was something that was available quite early on in Isabelle. And also things like the ISAR proof language, which we'll also see of. The first version of that appeared at the end of the 1990s. So we're already kind of seeing quite a little bit of, I guess, progress there. The 2000s was really kind of this kind of period of expanding kind of what proof assistants could start to do. So particularly for Isabelle, what was particularly relevant was Sledgehammer, which is the very well-known kind of press a button and hope it works tool that is quite essential to formalizing in Isabelle, and definitely one of its kind of key advantages even today in kind of the theorem prover space. And also start to get some really kind of major mathematics projects in computer science. So the computer science example, Cell 4, is the first formally verified operating system. That also came out there. And then kind of more recently, we started to see kind of a huge diversity in the kind of tools that you get. Some counter example finders, different kind of search tools, different extensions to Sledgehammer. It's really improved a lot since its first release, code generation, and many more. There's just a few kind of examples that we've seen out there. So, Isabelle, in terms of the basics, how it works. So Isabelle itself is a generic framework for a proof assistant. It just so happens that Isabelle whole is by far the most well used and well known. So generally when people talk about Isabelle, particularly for mathematics, they're referring to Isabelle whole. So that's the proof assistant built on the foundations of higher order logic. You might also hear occasionally people refer to something like Isabelle ZF, right, which is built on ZF foundations. So that was the kind of initial idea of Isabelle, is that it was this kind of more generic framework for proof assistants. It just so happened that Isabelle whole was really where the development ended up going and where most formalizations are placed. Automation, the key tool being Sledgehammer, that relies and calls out to a number of external theorem provers, as well as we've then got internally more automated tactics as well. Different search tools. So particularly these last two, Find Facts and Therapist, they have both come out of relatively recent research in the last few years, kind of helping to tackle the whole how do I search more of natural language and find things? And I'm mentioning these, and I'll show you these, particularly because even if you don't end up using Isabelle, if you're using Lean and want to find out, hey, has this been done anywhere in Isabelle? These might be tools that are quite useful for you in terms of searching those. So structured proof language. So we also have a tactic kind of style proof language. I'll show both. But I think in my mind is one of the key advantages of Isabelle for formalized maths, just in terms of how you can use it. We've got two IDEs, finally. Our main one's JEdit, and that's actually what I'm still going to use today, just because it's what I'm used to, and it's also, I think it's the most stable. We do now have a VS Code IDE based kind of framework as well, or Codium based editor. It's mostly there, but I haven't personally used it, but you might want to experiment with that. I have seen people use Vim as well, so you never know. Archive of formal proof. So this is our big library, and then all these additional features that have come along. Yeah. So this is the archive of formal proof. So just to kind of give you an example, this is the archive of formal proofs here. If you bring it up in your website, particularly what you might be interested in doing from a mathematics standpoint is going to topics and then go down to this mathematics area. And that's going to be an easier way of kind of exploring some of the different kind of libraries that are out there. It's interesting kind of to mention that if you kind of click and you go to kind of explore some of these, sometimes they're quite, there's quite a lot in here. So you can download the kind of entire proof doc. That's 157 pages of proof that's in that entry. Sometimes you'll get other entries that have 2 pages of proof, right? So the archive of formal proofs is very much it's an archive, right? It's not intended to be somewhere where you're continually updating it. It's not like MATLib in that sense. It's very much like, I finished this piece of work, I want to upload it to the archive so that people can go back and refer to that as a library. As a maintainer, so I don't maintain AFP, but as a maintainer of my own kind of entries on the AFP, if I make minor changes, that's usually quite permitted, usually with a note, so that anyone referring to your entry can see if anything might have changed that affects their own proof. If you're making significant changes, so say you're doing a refactor in terms of how you want to formalize a mathematical concept, the general idea is that you re-upload, you have a new entry, right? So that's kind of a backwards compatibility situation. So that's, I guess, very much the first major, I guess, difference formalizing mathematics in Isabelle compared to Lean, in that you're going to get multiple versions of different topics. And I see that as both an advantage and a disadvantage, because there are obviously times where formalizing a mathematical structure one way makes it easier to do certain types of proof, whereas the other ways it makes it harder. The key challenge then for us is to maintain the connections. So you can still translate some of those results depending on your different representations. And that's very much up to the author as to if they've come up with that or not. Those are just things to kind of consider. But yeah, so you might want to go and explore the AFP a bit. And these are some examples of some of the search tools out there. So Therapist is here. This was more of a natural language kind of based search. So you can put in like different concepts. So say, for example, if I wanted to look up graph theory, I could put in graph theory as a concept and just do kind of a search there. I haven't tested this for a while, so see how long it takes yet. And you can see it starts to come up with different things. you can also do things like, I'm not interested in graph theory results from this theory because I know that that's kind of less interesting to me, or that's more applied. So you can start to customize this a bit. Yeah, those are a few of the tools that we've got. So that said, I'm now going to jump into a little bit of a demo just to give you a little bit of an idea. If you have any questions, please feel free to stop me and ask them, all right? So we can see what's going on. Cool. So this is Isabelle J Edit. This is what we've got kind of coming up here. There's a few things that I guess we want to become familiar with immediately when we look at this as an editor. So on the side here, this is where I can navigate all of the existing kind of Isabelle distribution folders. I find that quite useful to have up and to be able to see, but you can also, obviously, once you know what you've got, get that out of the way. And then we've got these two kind of main sections of panels plus the main kind of IDE kind of environment, right? So down the bottom, this is where our output panel is, where we keep track of our proof state. So it's a little bit like what you were seeing in the info view for Lean, right? So there's a kind of similar area there. Query is the kind of old search tool that was built into Isabelle. This is your Sledgehammer panel. So Sledgehammer, these here are the external provers that Sledgehammer is calling out to when you do a Sledgehammer based proof. And yeah, you can change those if any of them are causing you issues. I basically never have. I've always left them like that. And these are your symbols all in one place. So if you don't know how to write a particular symbol, you can always just kind of navigate down the bottom here and hover over it, and it gives you kind of the symbol that you might need. So you can see what and get used to the shorthand after a while. So those are your kind of key panels on this kind of bottom section. You can, of course, move these around and customize them a bit. Over on this side, we've got a few things. So the key ones are things like this theories. This is usually the one that I have open. So what you can see here is that Isabelle examples is currently the theory that I am on. It's got this kind of little bit of pink there at the end. That just means that I haven't kind of gone through and kind of checked everything. And now I scroll to the end and I'm at the end of the theory and it's processed everything. Okay, it's come out fine. So if you've got any proofs in there that have or that have not been proved or things like that, it will usually show up in this bar. If it's either hit a point where it starts the loop, or if it's hit a point where you're trying to prove a theorem and there's an error and there's a proof that hasn't gone through. So you can see that in this side panel here. This also shows, and the reason that we've got so many things on the side is all the theories that I have currently got loaded into kind of my Isabelle environment. The reason that I've got a lot of theories sitting on the side here is because the second lot of examples I've got, I'm using a few analysis tactics. So when you first open, especially the second theory in Isabelle, if you do try that out for yourself, the analysis library is huge in Isabelle and it can take a while to build, and it's not pre-built or anything. When you first open it up, Isabelle doesn't need to build it. Isabelle's generally very fast. We generally don't have the processing time issues that Lean has. That said, the analysis library is just big. So it takes, a few minutes of sitting there, and then it will slowly, and you see it work through the different theorems as it loads each of those in. So you can keep track of kind of how far along it is. At the moment, I've kind of loaded the whole probability session. I've got a pre-built image of that on my computer just because I use it all the time. So I don't want to have to wait a few minutes every time I open Isabelle. Yeah, so yeah, that's kind of how this is laid out. Making sense so far? Okay. Excellent. So now we can get to the actual interesting part, which is how we do maths. So this is the start of a theory in Isabelle. You always start it with theory. Your name here has to be the same as the file name, which has to end with a .thy for it to be recognized as an Isabelle theory. So you get the Isabelle syntax highlighting. All right. So that's a common error when people first start, is that they misname the theory. You then have your import statement. Imports main is usually, if you're getting started and you not doing anything particularly complicated, you just import the main library, and that imports everything in kind of the main distribution effectively. So again, if we're looking at our kind of file browser on the side, what that's importing is all of these files that aren't in a folder. That's kind of what's in main usually, right? So anything in a folder, you might need to import, say, I want analysis, so I'd import whole.analysis as well. So basic import statement for what libraries you want. And then what we're going to start with, given we covered some logic yesterday in Lean, I thought we'd cover some logic in Isabelle today, just so you get an idea of some of the kind of basic tactics that we have. So firstly, this is taken a little bit from my logic course, so that's what some of these rules refer to in terms of natural deduction. But if you click here on the side, this THM command is quite useful because it allows you to actually see the theorems printed out, right? So if you just go theorem this I1, or if you see a theorem in a proof that's being used in a proof and you don't know what it does, this is a really easy way to instantly see what does this theorem actually state, right? You can also, of course, click on it and go to where it is and see the proof itself there. These are all pink because some files are locked in Isabelle, so you can't actually kind of change them. That's what it's doing there. But this is an easy way just to see it in place. Cool. All right. So then if we start to look at some logic examples, so the first thing that I'm going to show is actually some things that aren't true, because that's something that we can also do in Isabelle, right? There's two counterexample kind of checkers in Isabelle that are both quite powerful. Nitpick is probably the one I most commonly use. Quick check is also built in. So if you ever have a theorem that you're not quite sure if this is actually true or not, you can plug it in here and try nitpick, you know, and it's obviously it's a counterexample generator. It's not complete. It's not going to tell you this isn't true, that we need a proof for that. But it does quite often come up with things that I wouldn't otherwise expect, and particularly often catches side cases in proofs that, you know, I might have forgotten an assumption when I'm starting off. And so it can be quite useful when you're kind of starting off with proving something to have that there. Oops is not our sorry. We also have a sorry in Isabelle. So sorry is where, like I think Lean, where you have a statement, but you're pretty sure it's true, so you put sorry there, and Isabelle just kind of accepts it. And you really hope that's not a mistake later on when you've got most of the way through the recipe proof. Oops is generally when you have no idea if this fact is right. You just want to put something down, and you want to be able to keep typing other things in the file for now. And so when you do oops, it hasn't added this to lemmas that I can use or anything. It's just going to let me keep working in the file. So yeah.
Is it like specific for logic, or we also do it for?
I do it for combinatorics, for numbers, for anything. Yeah,
it's able to catch up. Maybe if something is not true for 0 and equal to 0.
Yeah, absolutely. So nitpick and quick check are both quite good for that. Even like arbitrary types.
This exists in Lean, but only for a very small number of types.
Yeah, interesting. Yeah.
It's called, I think, slim check in Lean, but it needs a lot of work.
Yeah. So there we go.
But it's great when it works.
So those are a few examples. This is just in logic, but yeah, you can definitely do it in another. So now let's have a look at some logic proofs. So these this first one here, this is in your tactic kind of style language, which you're kind of used to from Lean, right? Very much looking at applying different rules and how we might use them. So if we can see down the bottom, this is our sub goal that we're trying to prove. The first thing that I want to do is I want to be able to assume kind of what's in the front here, right? So I want to assume this thing before this big arrow. And this double line arrow, it's kind of Isabelle's meta logic. So Isabelle kind of has two levels of kind of the logic. It has Isabelle's kind of meta logic, and then you have kind of logic statements, right? Which are terms that you're actually talking about. So generally, if I have a series of assumptions for a proof, I'm going to separate them by this line here, right? And it just slightly changes how you use the tactics. I'm not going to go into a whole lot of detail for that just because of time, but yeah, happy to answer questions later. So what we can see though is that if we kind of first do this imp I statement, which is your implication introduction rule, right? what we do is it changes our statements. And now these implications that were at the end, rule kind of works backwards, and it now changes these both to be kind of double line arrows, right? So this means that Isabelle now knows that this is not kind of a term with an implication. It knows that these are individual assumptions, right? We have this is an assumption, this is an assumption, and this is an assumption. And so plus effectively applies that implication introduction twice. So it's applying the same rule so that we turn these 2 arrows here from the back of the proof until it hits kind of as far as it could go with that goal without encountering something else from Isabelle's meta logic was something there. And then we kind of want to work forward because we want to get rid of the implication kind of in our proof as well. So this is now where we have an E rule, right? Your elimination rule kind of thing. And implication elimination. And moving forward. And so we can see what this does is it kind of splits our proof into 2 parts now. So one is looking at, well, if we have P and Q, and one is looking at, okay, the kind of the other case effectively. So moving in both sides. Conjunction splits that first proof goal into the 2 things. And then at this point, what we can see is that you've got your assumption. So P is an assumption and P is the goal. So when you apply the assumption tactic, Isabelle just matches that up. The matter of it is that I would basically never use these rules unless I was teaching my first year logic class, which is when I use them, right? Because most of the time, all I would do for this is just by SIP, right? Or by any kind of automated tactic. And this is kind of the first example of what happens. You could either call sledgehammer and that would respond really quickly by like going into this panel and pressing that button. Or especially because I know this is quite simple, I don't want to even have to go to the advanced tactics. I don't want to have to call out to any of those advanced kind of theorem provers. I just want to try the local tactics. So try 0 just basically goes and tries the different local tactics and sees, oh, okay, I can prove this statement using all of these kind of different things. So try 0 is usually what I would try first if I think that the proof should be fairly simple for one of the built-in kind of tactics in Isabelle. And yeah, that gives you an idea of some of them that are out there. And you can see a few familiar things, right? We've got a Linnereth, we've got a simp, different things and different levels of power. So just kind of as an example of what I meant by an ISAR proof language, it's also very rare that I would nowadays, especially before submitting to the AFP, end up with an apply style proof where I've kind of got to think about, okay, that's going backwards, that's going forwards. Like, what am I doing? I need to keep track of what's going on in the output state. Usually what I would use is the ISAR language, which is basically instead of having to look at this output state to keep track of what each apply style rule is doing, so I know what I have to do next, I can kind of read it, right? And that's kind of all that the ISAR proof language does, is it takes what you kind of were keeping track of in your goal panel and puts it actually into the proof. So it feels a little bit more natural, I think, in some ways, especially if you're coming straight into theorem proving. So this is starting off by going, okay, I've got this statement. I'm going to start off by assuming that I've got this. I now want to show this statement. So it splits that into 2 parts. Splits the assumption that's before the logic kind of arrow and my conclusion, so I can refer to that easily. And then proof, I know that this is showing an implication at the end, so I can still apply a rule if I want to, kind of within the proof. And so this now kind of let me say, okay, I know I want to assume the 2 things before the last kind of double arrow, and I want to show the last thing after the double arrow. And I could move through this all again. An intro and a lim are just slightly more powerful introduction and elimination tactics than rule and e-rule are effectively. Again, I would very rarely use these in practice, but it kind of just to give you an idea of what's kind of going on underneath the hood. So auto, for example, has the introduction, has elimination. It's all built into it as a tactic. I would usually just use that. Yeah, so that's kind of some basic. So those are the 2 styles of proof that we can do in Isabelle, your tactic driven and your ISAR driven proofs. Going for time, okay. And yeah, so this is kind of showing, oh, I can do this a number of different ways, right? And this is, for example, again, usually because I don't want to have to worry about splitting around the meta logic or whatever like that in my proofs, usually I would use these kind of things. So I'd actually state the assumptions explicitly in the lemma statement. I'd use shows to make it very clear to Isabelle what the conclusion is. And I can do different things there. And that just starts to make the proof a lot nicer straight off. Yeah, so there's a bunch of other proofs in there just with the logic rules. Go through and play around with if you want to in your own time. So let's have a quick look at some basic maths. So it's you know, basic kind of theorem, right? Cantor's theorem on surjectivity of a function. And there's a number of different ways that we could write or prove this in Isabelle. And this is just a nice example of kind of different ways you can use the ISAR proof language depending on your style of proof and how you might approach it. Again, this can be done automatically, right? So it depends on how readable you want to make the proof. And this is something I would say keep in mind if you're ever looking at an Isabelle proof. There are times where I purposely don't delete an ISAR step that I probably could, just because if I want to go back and look at that proof later on or learn anything from it, it really helps if I have that step in there so I can understand what's going on in the proof, even if a tactic could potentially do it for me. So there's kind of a balance. There's cases where you obviously want to get rid of anything that's unnecessary. There's also cases where for readability and maintainability, it can be nice to leave it in. So yeah, these are a few kind of proofs that we have here. Pretty standard kind of things. So this is a proof by contradiction effectively, right? So you're assuming it is true and you're showing false. And you can structure this in kind of different ways. You can label your assumptions if you want. From that assumption, we establish a new fact, which we're labeling 1. We're just using the simplify tactic, and all we're doing there is adding in the definition of what surge means, and that's all it needs to do. Again, if you were ever looking at a proof and you were like, oh, what surge def actually mean? You could go in here and type theorem surge def, and you could see kind of how it's defined. Yep.
So what does the from 0 do? Like, does it work if you delete the from 0?
So if you delete the from 0, it doesn't know that we've got that surjectivity assumption in our context. So this line, for it to work, because it's using that surjectivity definition, right? It's unfolding or, you know, simplifying based on that. It needs to know, well, what fact do I have to work from? So there's a few ways you could do this. From 0 is 1. I would probably not do that. That is a later example. I would probably just do then have. Right, I have an assumption, so then have this next statement. There's lots of different ways you can do this. And for example, if this was a more complicated proof and I had a bunch of other stuff in between that assumption and this statement that I was doing, it can be quite useful to say, okay, well, from this line up here, we now have this.
And so I guess, is the blast like it's a decision procedure for logic or something? And it will not de facto use the hypotheses. You really have to say, use the previous hypothesis now.
Yeah, so generally, that's the case with most of Isabelle's kind of tactics. If you need to tell it kind of, well, what's it using, unless, say, for example, I'm actually curious whether this can just do it by simp. No, it can't. So sometimes definitions are in the simplifier already, so you don't, if a definition's already in the simplifier, you don't need to explicitly add it to the proof. But yeah.
It's saying use all the hypotheses I have so far.
So none of they're introduced in the proof themselves. You could go like from 0, 1, 2, for example, and you specify the different labels. If you have assumptions kind of in the start of your proof or in your lemma statement, you can go from assumptions, and that will capture all the assumptions so like those that assumes that actually in the proof body. So if it was up here, then it would be like that. Yeah, cool. Yeah, this kind of shows you how some different ways that you might write this. So this, for example, has a this, right? So from this refers to the thing that's most recently a hypothesis in your kind of environment there. And then, yeah, this is another even kind of simpler kind of version here, because at this point, we've put that assumption in the actual lemma statement. So this is just actually, this last example is how I would write probably this proof, because it makes the assumptions very clear. It makes what I'm trying to prove very clear. It's also separating some of the typing thing with the fixes statement kind of at the top. So I'm kind of saying, oh, I'm working on a function from dash A, some arbitrary type, to a set of some arbitrary type. So it's a little bit neater, usually liked. And yeah, so here there's a few different ways that we can do this. So I would probably also use this obtain step. Obtain is, instead of proving that you have exists A, you can just say obtain something that works from this type, to obtain an example where this property is satisfied. Yeah, just to kind of get rid of some of those little local quantifiers. So a statement like this, or a for all, your typical for all symbol within it, they can both make Sledgehammer complain when you start doing more, not complain, but Sledgehammer's just not very good at dealing with internally kind of quantified things. So if you can kind of get rid of that by saying, oh, obtain something where it's got this property, that's an easier object for Sledgehammer to work with and the automation to work with. So that's usually what we want to do. Yeah, so those again, hopefully good examples. Cool. All right. Going to quickly jump across to show some tactics. Preemptive by saying, this is not the kind of work that I do, but it's kind of some simple examples of mathematical kind of statements that you might see. So for example, this is really just kind of give you an idea of what some of the Isabelle tactics can do. I'm not going to go into all of the proofs in a whole lot of detail, but this is kind of a nice kind of long proof, just with a bunch of, powers, multiplication, etc. We've also got something probably a little bit like the lean simps tactics. So this algebra simps, and it effectively has all your kind of common kind of rules that you have built in here. So passing algebra simps into the simplifier is actually quite powerful usually as a move if you've got a purely algebraic manipulation that you've got to do in a proof for what's going on there. This is actually also using, I'm pretty sure, this proof here. But PowerSook, unlike all of the rules in algebra simps, this one here is actually already in the simplifier because of where it's declared. So you don't need to do anything, like you don't need to specifically say use this. Isabelle kind of knows to use that already. But if we don't want to include all the algebra simps rules in the simplifier because circular potential leading to that is not particularly nice. Yeah, this is another example with square roots. Again, this is mostly just using your simp tactic, which is actually still quite a powerful tactic in its own right. There's one point here, whenever you see an SMT, that's almost a guarantee that we've done a Sledgehammer call at that point, because SMT or metis, they're usually the two tactics that result from bringing in something and using something that an external theorem prover has suggested. Yeah, that's kind of an example that we might see there. Yeah, there's kind of just some examples of that. There's an approximation tactic, which is kind of also fairly decently powerful for working on different things. I have not used this myself because I don't really deal with real numbers in combinatorics, but other people might. SOS, which I think we found quite a sum of squares tactic. Again, that I think I looked that up. That was in a 2008 thesis. So these have existed around for quite a while in Isabelle. What we've got there. And then this last one here is your classic kind of square root of 2 is, not a rational number, basically a proof. And the reason that I've included this is that this proof, every single line that's been filled in here. So I might have typed, okay, I want to obtain a rational number, such that the square root of 2, which is of a real type, that's why I have to use this of rat that lifts a rational number to the reals effectively. So, okay, I say, okay, if I'm assuming that square root of 2 is in the rationals, then I can obtain a rational number such that this property is satisfied. And then because I don't want to figure out how to prove that, I just press Sledgehammer and it suggests this first one here. So if we wanted to do that ourselves, you could press Sledgehammer, or you can just do try without the 0, and it kind of suggests, oh, okay, this can be solved for us here down the bottom. Right. And this is, I mean, very much, I think, how I work doing formalized mathematics. It's often about less what tactic do I have to use here, but it's about, okay, how can I break this theorem down enough to the point where it's something that the automated theorem provers can actually help us with. So that's, I guess, possibly a slight difference in the approach compared to doing it in Lean, where I suspect you need to have a lot more knowledge of some of the different tactics out there, so you know what needs to be used in each case. That said, there are plenty of cases where Sledgehammer is not going to suggest do something, and I look at it and I go, that's so obvious. This has to be able to be proved by the simplifier. And in that case, sometimes it's about just giving it a few suggestions, right? So maybe it's, well, I'm pretty sure that this is just a basic kind of commutative kind of property that should exist out there for my natural number type. So I'm going to go and do a quick search and find facts for what I expect, find the lemma that I'm pretty sure will work, and I actually give it and I go, okay, using this lemma, and then I try Sledgehammer again. And fingers crossed that time is actually being able to figure out, okay, with that, yeah, all you need is the auto tactic if you are using that. So it's not complete by any means. It's definitely not, if Sledgehammer fails, it doesn't mean there's no proof. It just means that you either need to suggest something to it, or maybe specifically instantiate a parameter in kind of one of the tactics. So for example, in this one here, what you can see down the bottom is that Q, it has this query mark in it, right? So Isabelle has to kind of figure out, well, what am I putting in there for Q? And in this case, what I kind of probably wanted to put in there is this square root of 2. So if I wanted to specify, I could type it in specifically, say, oh, I want to use square root of 2. And you can now see it's kind of updated this thing that I'm using to actually instantiate it specifically with what I want. And that will make it easier for a tactic like blast or auto or simp to process. So you can still customize it if you need to. A lot of cases you don't need to give it the parameter, and Isabelle's smart enough to figure it out for itself how it wants to instantiate those variables. Yeah. This is a proof that I think if you look through it, it mostly follows what you would probably expect someone to do on paper if they were proving this kind of for the first time. And most of the actual kind of nitty-gritty parts of the proof that you don't necessarily want to see on paper, I think that's so that's quite nice. One thing I will also say is that this is very much a matter of pressing Sledgehammer after each statement, right? If I was going to say do something like this and then submit it to the archive of formal proofs, or I want to just make it a bit simpler, a little bit easier to read, I might do things like, oh, okay, if I'm looking at this, maybe there's a lemma in here that if I give it a few of those hints, I actually only need the simp tactic or only need the auto tactic. Nowadays, SMT is pretty reliable as a tactic. About 5 or 10 years ago, usually if you could find something that wasn't SMT, that was quite preferred by the maintainers of the AFP. Nowadays, no one really cares. That said, it is often the tactic that will take the longest. Again, that might mean a few seconds, which isn't a lot, but from an Isabelle standpoint, that is a decent amount of time. So if you can find a simpler tactic to do something, you might want to do that. So Sledgehammer can also be quite useful in just terms of, can I prove this? Okay, I can. That's a messy proof. How can I make this neater using the lemmas that it's suggested and found for me? So that's as you get more experience, people start to do that more. Yeah, that's kind of a few examples there. Right, it's still making sense, hopefully, and people following along. So I thought what I would finish with is, in terms of some kind of Tory examples, is some graph theory, because that's what I do. So I like graphs. And this also gives me an opportunity to show you a little bit about a thing I've used a lot in my research called locales. So locales are a little bit like lean structures. I think they can do a little bit more potentially, but so they're definitely not type classes. But I think they're a bit more powerful than lean structures, particularly in terms of inheritance, rewriting, and those kind of capabilities that are out there. So I personally use these a lot in my research, because while Isabelle does have type classes, it is an advantage and disadvantage of Isabelle's simple foundations. We can't do some things that you would want to do naturally in a dependent type theory, right? So say, for example, if I want to declare the type of, integers mod 2, field. You know, that's something that's quite hard in Isabelle because that's got a dependency on this too, right, on this n, right? And that's an extra kind of dependency in terms of a type. And so you have to do some workarounds when you're doing some things like that. Similarly, there were some things with groups. So the initial algebra library in Isabelle that most people still use, a group, the structure itself was defined as a record type, but we had to leave some extra fields open so that you could later kind of extend that to rings, etc., which is just a bit messy to kind of work around with. Possible, but you know, a little bit annoying. So I personally really like locales because they don't come with a lot of the kind of fluff that you have to deal with when you're dealing with type classes. There are one or two kind of things that are harder in terms of using them, but as soon as you're working within a locale context, it's a very natural way of doing proof. So effectively, all it's doing is saying, okay, I want to declare a new context or a new kind of locale or object kind of thing. It's going to have two parameters. It's going to have a set of vertices, which have some arbitrary kind of type here. And it's going to have a set of edges, which are basically, I'm just modeling as sets in their own right. And then because I want this to be a valid graph, I'm going to assume a few kind of core facts for this thing to be a graph. One, each edge has to be a subset of our vertex set. And two, each edge has to have a size 2, right? So each edge has to have 2 vertices. So I can now kind of use this as I kind of want to in my environment. Specifically, I can do a lot of proofs about graphs within the graph context. And then it's very natural. I'm using these parameters as I would on paper, using these assumptions and basic properties as I would on paper. I can also do a lot of different inheritance things. So I'm not going to go fully into that now just because of, again, time. This is one really simple example, right? So if I wanted to extend my graph so that I also can model weights on an edge, right? That might be a simple matter of adding a weight function. This is a very simple kind of example. I would probably do this in a nicer way if I was doing it myself. But just kind of an example. This is direct inheritance. It takes everything that's already in the graph locale and it adds an extra parameter. And similarly, you can add extra assumptions as well to a locale context. You can do indirect inheritance, which I find quite useful. I'll often define another new locale and go, oh, actually, that's a type of that structure. So I'm just going to establish an inheritance, and it automatically means that I can use everything I've previously proven into this new one. If I say, well, actually, you know, I've done a lot of work between design theories or set systems and hypergraphs, similar, basically the same underlying object, just different names that people want to call things. And so the locales allow you to rewrite things. So you get to inherit everything, automatically rewriting all the definitions to use the ones you want in your local context. So I found locales also a very useful tool, actually, in terms of going, well, someone's modeled graphs that way using relation. I want to model graphs using sets because that's easier for me to work with. I also want to make sure that they can both inherit everything from each other. And that's something that I could do using locales. These are kind of some of the things. Yes.
What exactly is this weight here? It is going to be a function.
It's a function from some set of this type dash A to a natural number. Again, it's probably not how I would do weighted graphs in practice because I'd probably want to have a label on the edges in case edges had multiple edges.
I think that you would want it to be from the specifically the set of edges, not just some set.
So what this is it would take so functions in Isabelle tend to be total. So it would take it needs to take something. So this is kind of the type of the weight parameter. And then it might be just that, so whatever you kind of gave it would work. You're probably only going to pass this weight parameter though, an actual valid edge. And if you wanted to kind of specifically limit and say, hey, I want to give an invalid weight, right, to something that isn't an edge in my graph, you could add an extra assumption to this here, right? But the type itself, again, you can't kind of issue kind of dependent types. So the types tend to be
Kind of
big.
more extreme version of how in Lean we have like the division has to be defined everywhere. It just gives trash output something to you.
A little bit, I think, yeah. So yeah, that's kind of what we've got there. Yeah. So these are like some basic definitions. So a definition is just to kind of declare what's kind of going on. So for example, are the vertices adjacent, right? This takes two elements. It naturally uses that parameter kind of E from my graph, and it just returns a Boolean value. You could probably also just put that as an abbreviation. You could probably just type that as well, however you want to do it. This is the flexibility. The definitions are very declarative often, right? So you're saying, okay, you know, let vertices adjacent returns this, right? And we can do some pretty simple kind of lemmas on this. So I put this kind of together mostly last night as just a quick kind of toy example. And often when I would be starting a proof, if I didn't know what I was doing here, is I would go, okay, vertex adjacent definition is all I'm using. I probably am going to need to unfold, right, that definition. And when you start typing, Isabelle sometimes suggests things. And so you can kind of just tab and fill that out. So this is just kind of to give, you know, it a hint that this is what I want to do. This is quite simple. I might have even gone, oh, I should try just by simp, you know, and see if that works. Okay, that's not working. No proof found straight away from trying all these tactics. But again, if I went try, it straight away kind of suggests to me, okay, you should use this insert commute, and I can just click on that and it straight away fills in kind of what's going on here. And then again, if you want to check what that's doing, control click takes you to where it's proved. And it's just a basic kind of lemma on sets. So this is kind of, that's the process I would usually follow if I was proving new definitions. If I had added that vertex adjacent definition to the simplifier, which I probably wouldn't, but then I wouldn't even need to give it this. It would figure that out for itself. But I find it's quite useful often to unfold a definition when I know it's something that Isabelle could figure out if I'm not hiding information from it. So those are a few, yeah.
Whenever you make a definition, Isabelle will add theorems about your definition.
Sorry, I should have covered that. So whenever you make a definition, this def underscore def kind of lemma is automatically kind of added so that you have that on hand.
Very much like Lean does with structures.
It's very similar to what's going on there. Functions, that even more happens there. So definitions are usually these quite kind of easy to follow, kind of declarative. This is what it means. A function is usually a recursive function, right? Functional programming. So for example, if I wanted to, you know, calculate all the kind of, you know, edges, for example, that I want to turn a list of vertices into a list of edges. And that's what this kind of function here does. Fun actually gives you a whole lot of extra kind of useful definitions that you can use. It will usually give you an induct lemma that you can use. It gives you a simplifying kind of lemma that you can use. So it gives you a bunch of different useful things that you can kind of use and see about it when you declare fun. And usually if it's a simple enough function, Isabelle will show that it's a terminating function in its own right. If it's more complicated, you need to prove that. And so we can also start to do like some different elements on here. And so that's why I've included these in the file. These are like some examples of just induction in Isabelle, right? So what this is saying is I want to apply an induction rule on the list XS. And the rule I want to use to do this induction is walk edges dot induct. So that's using the induction rule from that walk edges definition. If I didn't have this here, it will try to just apply a kind of naive list induction effectively, because it'll figure out XS as a list, and then it will try to apply the basic kind of based on how a list is defined, because a list is an inductive structure, and it'll try to just apply that rule. And you can see that that's not really giving us what we want from an induction kind of principle. So that's why it's quite often useful to use these kind of custom induct rules when you're doing rules on different functions declared effectively. So yeah, so there's a huge number of kind of examples there. Some of these, so something like simple add that applies the simp goal, the simp kind of tactic to all of these kind of remaining goals with the added information about what the definition is for the walk length function. So that's all that this tactic is doing as an example. So that's something that I would write myself. And that probably is something I wrote myself, right? So I'm saying I'm pretty sure simplify should be able to do this if I give it the definition for what I'm proving something on. Whereas you can see down here, I've got this meta tactic that's being called. So that's probably a sign that I got to this point, applying simp didn't work. And so instead I did a call to sledgehammer so that it could suggest something for me instead. Yeah, that's kind of most of what I had in terms of some examples. So there's plenty more here in the file if you are interested to go and have a look at. But hopefully that gives you a little bit of a taste in terms of what Isabelle looks like for some kind of basic examples. So I will jump back to this. I've got 8 minutes left, which is definitely not enough to go through anything substantial from a research standpoint. But what I might kind of just give you a little bit of a taste of is to finish off is some of the kind of research that I've done using Isabelle. Mentioned kind of with the project yesterday. So the last thing I focused on in my thesis was on formalizing this probabilistic method. And my focus with my thesis was very much less about, I want to formalize this really well-known theorem. It was instead, okay, in combinatorics, there's all these kind of techniques that we use and we want to apply them over and over again, but in different ways that also aren't always immediately obvious. So how can I formalize these kind of techniques and the basics that we need so that it's easy to apply these kind of concepts over and over again? So this was specifically one of the areas because I was quite interested in graph theory and hypergraph theory. Probabilistic method is a very well-known kind of approach. And it's got a lot in it. There's a lot that covers. So there's a lot of different techniques within that. So yeah, just to kind of throw it. This is a basic proof, something that uses the probabilistic method, right? So we introduce some kind of randomness by coloring the vertices of our hypergraph or graph by 2 colors. We then kind of define an event kind of. Clearly this probability is that. Sure you can see where that's going. And then some basic kind of inequalities. Yeah, so nice little 5-line proof. That'd be nice to do in 5 lines, wouldn't it? And so yeah, let's get started. That was 1 line of that proof on my very first attempt of just kind of hacking away at it, right? It was taking me a lot of work, mostly because clearly it was a very big lie. And that probability kind of took quite a bit of calculating. It actually brought up a really interesting thing I've noticed around intuition and probabilistic reasoning that I think I mentioned to some people around kind of independence being quite circular in terms of how mathematicians reason on independence between events, and kind of almost often like, oh, these events are obviously independent because, you know, you're referring to that physical intuition that you often get. But we need to use, instead of just using the multiplication rule, we need to prove it satisfies the multiplication rule. It takes a little bit of work. So it's kind of, I'm skipping through the slides just to kind of give you an idea. My kind of key idea was to say, well, how do we do this on paper in terms of using the basic method, and how can I do that? How can I structure proofs to do that in Isabelle quite nicely? And so these were kind of the 4 steps that you kind of saw as the basics around most things. And often this step 3 had a lot of other techniques and calculations that were going on in there. And I wanted to see, okay, is there anything I can do to generalize some of these steps in Isabelle? So one example is that first step, to introduce randomness in a proof assistant. It takes a lot of work because it's not necessarily a natural thing to, on paper, you do just say, you know, color things randomly or whatever. In a proof assistant, you have to define what the probability space is you're working on. And it's very rare that that would be done on paper, right? So this, for example, is how I introduced the probability space in Isabelle. Probability space is a locale, so I'm interpreting. That's what interpret does. It interprets an instance of the locale, probability space, with this measure M, which is a uniform count measure. And then this is a local kind of definition within a proof, which can be quite nice just to make the proof quite readable. And then I'm also, you know, just giving myself a few useful facts. Most of these are coming out by simple auto. I probably don't necessarily need to prove them. But sometimes, again, for automation's sake, if you can give Sledgehammer something saying, hey, I know that this is finite and I know that this is true already, that makes it much easier for Sledgehammer to find more complex lemmas that you might need that have those assumptions. So I was doing these at the start of every kind of proof that I was doing on the same kind of hypergraph kind of measure. So my aim was to generalize that. And effectively what I did with this was build up a full kind of locale framework where the locale itself kind of encapsulated the key kind of bits of information that I needed. And I did that quite abstractly. So this could be used to introduce a number of different probability spaces on hypergraphs. So one I obviously was working towards, I want a coloring space, right? Where my probability space is over the set of kind of all possible colorings of size n. But you know, this whole framework allows you to introduce a number of different probability spaces. And within that locale, it's kind of got all of those proofs. It's all hidden. So now instead of that big block of checks between each one, it's a one-line statement when you introduce that. A few useful bounds as well. I was kind of skipping through a few things here. And this is kind of the result of doing some of this work, just so you can see what a kind of proof looks like. So this was the proof on paper, and this was the proof in Isabelle. It's not too dissimilar, which is fairly nice. So you can kind of draw some connections. So you can see that first step, which was that really big block of text I showed a few minutes ago, we now just have this one line, right? Where instead of interpreting a general prob space, I'm interpreting a vertex color space, which has all of those useful facts around vertex coloring spaces kind of in it, and hidden away, and as you would. So it makes it much more natural to use and refer to that like you would, I think, on paper. Define the event, do a calculation. Calculation still takes a little bit of work. That's usually the step that I couldn't generalize as easily. And then that obtain step uses some of those general lemmas again. So the bits that I could generalize of this proof, namely steps 1 and 4, became significantly shorter. And even within 2, that also became shorter. So that was a lot of what you saw, that really big calculation on the first page was doing these calculations. And if I look at this, let me try to find, it's been a while since I've looked at this. Here. So this first line here, 3, that first 3 have PE. That's a fact about basically calculating the probability of that clearly statement, that clearly this is equal to that. And what's quite nice about this is now, instead of this being something I wanted to prove every time, this is actually a lemma that I've proved separately within the vertex space kind of locale context. So it's a little bit more like, again, what you would do on paper, saying, well, okay, I know I'm reasoning over kind of monochromatic edges. So I just want to get that calculation that I know is going to be true whenever I'm reasoning on events around monochromatic space edges. So yeah, there's a heap more in here, which I'm happy to show anyone who's interested. This was particularly interesting in terms of circular reasoning with independence, caused me quite a few issues. And it really kind of highlighted to me and the big parts of my work and of what I like to emphasize studies, no matter what proof assistant you're working in, is these kind of modular and reusable tactics really do make your proofs nicer. And I think everyone else really likes you for doing that as well. MATLAB maintainers probably like you for doing that as well. So it's definitely kind of this interesting balance between practicality and generality, just to make something quite usable as well, that I was often kind of balancing. So if you are looking at kind of proving something, if you can see a way of generalizing either a technique or a lemma or something within that, definitely do that rather than hiding it within a whole lot of layers of kind of applied tactics, because that might make it easier for your work, a bit that you wouldn't have anticipated, to be reused by someone else. Yeah, so to, I guess, finish off a little bit of a summary as to, like, why do I use Isabelle? why is Lean also out here, and what's kind of going on out there? So I guess I started using Isabelle as my first proof assistant. I started my PhD in 2019, right before kind of Lean really started to take off in terms of a mathematics proof assistant. I was also Larry Paulson's PhD student, and because he created that, I wasn't really given a lot of a choice. No, in all honesty, plenty of people in our group did start playing around with Lean, and it was completely fine. But I also really just quite like Isabelle as a way of working. I think for me, the automation really helps me. It's part of how I work now. And so that's something I'm quite used to. I also really like the readability of the proof language. I like being able to look back at my proofs and understand what's going on with them. And those are two things that I think I would particularly miss if I was to switch across to lean, as it is at the moment. So the simple foundation can often work in Isabelle's favor. It can also result in a few workarounds. I'm yet to encounter something I can't do in Isabelle because of the simple foundations. There's several cases where our group, like my group at Cambridge, did do things like schemes and that kind of thing, kind of in response to certain challenges. So we can do certain things. Sometimes just does require something that might not look quite as neat to start off with, but works quite well in the end usually. Definitely the automation. Huge amount of libraries. Analysis is still massive in Isabelle. And even though they're not necessarily as integrated, you can still use them. So there's definitely theories where I have seen, and I personally have drawn in archive of formal proof results from linear algebra, from analysis, from probability theory, and from combinatorics all into one place. And so it is still possible to do proofs that combine a whole lot of these different libraries that are out there. It is also nice that there's a lot for computer science. I'm a computer scientist as well, right? So for me, being able to do work and in an environment that's very easy for me to translate that into more of a program or algorithm related verification space, that's something I quite enjoy at the moment. And it's definitely probably up there in terms of performance, again, thanks to the simpler foundations. So no defender types to worry about. That said, some things to keep in mind if you do want to ever try using Isabelle. The libraries are a bit of a maze to navigate. That's why the search tools in the last 5 years have been amazing. It's definitely helped out a lot. And that's particularly, I think, helpful for anyone interested in just finding out what's going on in Isabelle. The fact that we now have those search tools as well. It is an older development, right? So the language is definitely not as nice as, you know, the lean kind of language. You have to do ML and a bit of Scala if you're going really into the back end, which can be slightly kind of nastier to work with. It is an older IDE, even though we do now have a Codium-based IDE as well. And it is, I guess, definitely doesn't have the, I guess, development support that something like lean does at the moment. Or the size of the mathematics community. I would still say we're definitely probably have a bigger program verification community. We still have a lot of people doing pretty amazing stuff in mathematics in Isabelle. It's just, yeah, size-wise, a smaller community for sure. So I guess given that all in mind, my personal view is that proof assistance, there's strengths and weaknesses for all of them, right? So I think that there's some things that if I was to do them, I would quite like to try doing them in lean. There's a lot of things that I would still want to do in Isabelle. And I think we're definitely, in my mind, not at a point where we've necessarily got the one system that we want to use for everything. Don't know if we'll ever get there either. There's different foundations, different things, and a lot we can also learn from each of them, which I think is also quite valuable. So for me, say, for example, some of the UI things I see in lean, I'm like, that would be a really cool thing just to have in the Isabelle IDE as well. And hopefully things go the other way as well. And something I personally found very useful in my PhD, when lean was starting to get bigger, there was one combinatorics file in MathLib when I started. There's now a huge number out there. So I often was spending quite a bit of time on the lean CILIP, you know, just to kind of see what's going on, learn from what people are doing, see how people have formalized different things, and slowly getting kind of familiar. So it's, if you're, doing a lot of formalization, getting to know things like search tools, search that kind of thing. That's out there. I think for Isabelle in particular, there's an advantage if you're doing something in lean, but you would like to see how something's done in Isabelle, especially hopefully with a little bit of an idea from today. That proof language is quite readable without even downloading Isabelle, right? So you can hopefully get a bit of an idea of what's going on just by downloading and looking at the proof documents online. So a bunch of stuff out there. And I also think there's a lot of opportunities for research comparing different formalizations, like maybe not necessarily as a key focus of people's work, but I think there's definitely opportunities out there for a few more. We're starting to see a few comparison papers out there in maths. I think that's something that there's more opportunities. So if anyone's interested in that, something I'm certainly interested in as well. A few useful links if anyone wants. I'm again happy to share these slides if anyone's interested. I've put in Larry's blog at the end that has a bunch of good introductory things for Isabelle. Fair warning, he does like to post about Isabelle and sort of things, but it does better compared to lean. But that said, I think there's a lot of quite interesting kind of stuff in there from resources. So yeah, if anyone's interested, I'm very open to questions now or afterwards. I'm leaving tomorrow, sadly, but yeah, you're welcome to get in touch as well. So thank you very much.